Research and Development Cell of Kannur University, in association with the Internal Quality Assurance Cell, organized a public lecture program on various topics from the 12th to 23rd July 2022. The first lecture was on the topic Affordable Clean Water Using Advanced Materials, and the speaker was Dr. Talapil Pradeep, Institute Professor, Department of Chemistry, IIT Madras.
Water is such a large thing, but you may say that it is a number of water molecules on this planet is constant or nearly constant. Just about 3.3 into 10 to the power 46 molecules. That's all the planet has. It is a billion tons of water that we have on this planet. So on the one side, water is constant, but carbon dioxide is increasing, as you know. So this is, on the one side, water is constant, CO2 is increasing, and it has consequences. But water is getting redistributed into products and services. Water is constant, but it is getting redistributed. And that redistribution of water into products and services is causing problems. And our current water crisis is a result of that problem in redistribution. And we will come to that in the course of this lecture. We, in our country, we use a very tiny bit of water per capita in comparison to developed countries. We use just about 980 cubic meters of water per capita per year. In comparison, some other country would use about 2,900 cubic meters of water per capita per year. So our water availability is about 1,500 cubic meters per capita per year. So we are using a sizable amount of water in comparison to water that is available, but somewhere else people are using far more water than the water that is available. So there is a big disparity, or we are far away, world as a whole, far away from equilibrium. This is where the water crisis is. And how do you address that water crisis? In every context, how do you address this beyond the scope of this lecture? So I will limit this lecture to that crisis in the context of drinking water, and how can we address this using materials, technology, solutions. So for this lecture, I am thankful to my dear friend, your Pro-Vice Chancellor Sabu, and Anil Ramachandran made all these arrangements. Thanks to all of them. I have several other affiliations. This is in a way to say that some of these what I about, you may have to take it with a pinch of salt, because I have all these connections also. So please do keep that in mind. Water is a triatomic molecule. It's just 3 atoms, 2 bonds, and 1 bond angle. So for a chemist, it is a very simple molecule. We must have understood this in great detail so that there is nothing else to understand. So it is such a small thing. But unfortunately, it has not been understood. Even today, we publish over 10,000 papers every year on water. Such is that complexity of this triatomic molecule that we have not understood it. Just last year, somebody came out with a paper saying that the surface of a drop of water can actually be metallic. Somebody came up with a paper again last year showing that a wire of can actually be plastic. You can bend it. Unbelievable is the diversity of this molecule. So water is, for those of you who are sitting behind and wanting to get into water, it is still fascinating. And we explore a few of these aspects in our laboratory. But when you start looking at water, this is the picture that should come to your mind. This picture is a picture taken on February 14th, 1990. This picture was taken by Apollo 1, and as you know, Apollo was sent by NASA to explore the solar system. And as Apollo went past the solar system, went beyond the Uranus, 2.6 billion kilometers away from planet Earth, it looked back and took a picture. And that is this picture which has been named as the pale blue dot. And the dot that you see is Earth, and the pale blue is nothing but water. And this picture very clearly demonstrated that water is the essence of this planet. This, you have heard it in many ways, including those written by Malayali writers. So water is the essence of this planet. And it is the most important inheritance of our planet. In fact, everything can be connected to water. I would say that our economic, social, and cultural outcomes can all be traced to water. This building is water, in the sense that the concrete stands here because it has 15% water in it. It is the strength of hydrogen bond that keeps concrete. This we didn't know. So water is the essence of this. Water is the essence of all this wood. As you know, water is the essence of everything else. Water is the essence of you and me and the sound. In fact, it is communicated because of the kind of water vapor that is present. So water is the essence in many, many ways, and power is water. Power is water. And one of my friends used to say that internet has a CO2 content in it. Same can be said about water. Water is the simplest and simultaneously the most complex problem of humanity. I do not have time to illustrate this. Everything simplifies to water. Everything simplifies to water. If you have water and if that can be used well, you have a healthy nation. If you don't have water, you don't have a nation. If you have water in conflict, you have nations in conflict. You have water that is distributed unevenly, you have communities in crisis. So water is central to everything, and you can write books on this. And let me say, today we look at water from this perspective of the Sustainable Development Goals. So among all the 17 Sustainable Development Goals, over 14 can be related one way or the other to water. No hunger, zero hunger. It's a water problem. Right? Inequality is a water problem. It is women or whatever is a problem of water. Life underwater is a water problem. Life above is a water problem. Clean water is a water problem. Sanitation is a water problem. What is not a water problem? So, this whole thing, I had a video to say that it is actually water. So, water that we talk about is very big, and I was just alluding to that point that although we have a lot of water, the problem is that water is not distributed evenly to everybody. So, in order to solve water problem in a larger context, what is needed is 3 S's. The S's are store, being sensitive, and smart. Let me illustrate this point a little bit. Store is to say that we have an average rainfall of 1085 millimeters, and that is 85th in a list of countries of 186 or so. So, we are getting a lot of water in comparison to Egypt, for example, which is the lowest, just about 56 millimeters of rain there. So, we are water reasonably, and of course, here we have water surplus. But that water is not stored. You see, it is surprising to see that we store just about 8% of our water, 8%. Whereas developed countries, the best of those countries, store something like 250% of water, meaning all the water that comes, and not only rainwater, but also used water is actually stored. And water is the biggest wealth that you have. And that is why people do this, and we don't have that. That would mean we need to have a lot of change has to happen in technology and our public policy in storage. Sensitive. The way that we have used water, we have contaminated our rivers, our water bodies. 83% of all the freshwater life has disappeared in the past 50 years. This is according to a study published in Science. 83% of all these freshwater species, we have made them disappear. So, what happens after 500 years? So, this is a big question. So, therefore, water has to be used in a sensitive way. We have to be water smart. Now, why is that we are saying water smart? And put all these into concepts into a few words. Let me say this, that for development, we say in order to have development, we need to use water, many people say. When you have development, you contaminate water. When you contaminate water, of course, you don't have fresh water at all, or fresh water is being stressed, and therefore, freshwater cost increases, production becomes difficult, cost of produce becomes large, and nobody can buy. So, this is a big cycle. So, increasing stresses on water essentially would mean that development will slow down. This is one thought. But then you see that there are countries wherein freshwater withdrawals have been capped. No more increase in freshwater withdrawal for economic activity. But economic activity goes up, GDP goes up. Here is an example of America. The graph shows that GDP of America goes up and up. The blue curve shows, for those of you who can see, at 1974, freshwater withdrawal has been capped at the 1974 levels. No more increased freshwater withdrawals. If you keep freshwater withdrawals constant, still keep GDP going up, how can this happen? This can happen only if new technologies come in so that the water that has been produced gets recycled. And this has happened, and economic progress is indeed possible, and that water is called peak water. Peak water puts a number of technologies into our midst. We need to investigate greater into this. So, it is a myth is that freshwater withdrawals have to increase for GDP to go up. Not the case. Now, that puts a lot of stress on our educational and research institutions to find new solutions. Now, this is not the only thing that I would like you to be aware of. I would like you to be aware of the fact that water is a big, big business. No, for a collected water network, for a collected network of water systems across the world, that includes freshwater supply, that includes wastewater collection, all of these, the cost is estimated to be about $60 trillion. So sitting here in this room, $60 trillion is very difficult to understand. What is that money? Let me give you a comparison. Count all the bridges, count all the buildings, all the roads, all the ships, all the aircraft, all the companies, all of these put together. This is called the collective wealth of the nation. India's collective wealth is estimated to be about 13.8 trillion. And the water network for the whole world is said to be about $60 trillion. We don't have that. So as a result of this, it is said that not even half of the world population will have all these collective network, even by 2050. Such is the large business opportunity in water. And to give you one more number, just for water sensors alone put in every home, every distribution line to measure water quality and quantity, well, the cost is estimated to be $1 trillion for India. So imagine how much of opportunity is there for us to innovate in this sector. So just to give you that as a foundation, we can discuss this further. How did you arrive at and all that? So when you start looking at this big opportunity, you also see a big social need. So this is our country with all the rivers. Smaller rivers are not there in this small screen, but all the rivers are contaminated. There is no single river in India which is not contaminated. And we monitor one river, the Bhavani River in Tamil Nadu. The entire river stretch is contaminated. And how much of biodiversity decline has happened in these rivers is a big issue. So it's not only this diversity and this contamination is the issue. Look at the top, India presents with lots of problems. On the top of India, we are at minus 45 degrees centigrade. Down south, it can be plus 45 degrees. On the east and west, we have the same kind of diversity in temperature, water, humidity, all of those. So India presents you with numerous problems, in fact, all the problems of the world in a basket. So if you have to have solutions, you have to have solutions which will work in all these diverse conditions. That, of course, presents you with opportunities too. You don't have to go anywhere to discover. You discover just in your neighborhood. We have all of these problems: arsenic, fluoride, uranium, mercury, chromium, perchlorate, nitrate, pesticides, antibiotics, plastics, detergents. You can count. So this is a huge list, and that laundry list also gives you a lot many opportunities. So on the one side, this is a problem. The other side, huge water problem is also there in agriculture. Indian agriculture is one which depends heavily on groundwater. 67% of our agriculture is on groundwater. That means that's a very huge groundwater decline, and this is seen by NASA photographs. On the left side, you have the groundwater at one time window, and the right side, just after a few years, this is what has happened. Now, this was done only in that particular region because it was possible technologically only in that region, but the whole of this country is being mapped today. shocking is what has happened. So, with all those background that I told you, so much has happened, what is that one can do? I would like to tell you that all our dreams become reality with materials. Every dream becomes reality with materials. So, for that I took a picture of this novel of Jules Verne. Jules Verne wrote this novel in 1865, talking about sending a man to moon. And this book is From the Earth to the Moon, 1865. In 1865, he thought about how do I send a man at the time when dynamite was there, and using all those rocket propellant science that we knew, how do we do that? To do this, you have to have a vessel in which you can put a human being. What would be that vessel which will carry a human being with sort of a strong vessel, but not all that heavy, so that you can send it? And obviously he took aluminium. You know, aluminium was discovered in 1825, but it was not produced commercially till 1879. Even before its commercial production, Jules Verne dreamt about aluminium and used that aluminium to send this man to moon. Although the novel talks about sending and all that, finally it did not end up in moon. It started becoming a satellite and went around moon. That's another story. Point is, he looked at aluminium. Our dreams become reality with materials. I dreamt about a dream, and I started looking at this with materials, and I am going to tell you a brief story of that in the next few tens of minutes that I have. So water purification has a lot of history, and all of this is to do with materials. I do not have time to illustrate this, but it is a story of materials also. And today those materials have become atomically precise. They have become nanomaterials, and the subject area is called aqua nanotechnology, wherein there are new adsorbents, new sensors, new catalysts, new phenomena, new devices, all of these. Now, if today we look at materials in great detail, these are nanomaterials. In nanoscale, every atom matters. So we study materials with atomic details, and for which you have a lot of spectroscopy and techniques. This is a particle. This kind of particles are being studied by several of my students. One of my former students is sitting here, Manju. So he used to study particles of this kind. And you put it into a mass spectrometer, you measure a mass. So this is one such peak of a particle. But to tell you that when you start studying this in great detail, you can study not just this particle, you can also study how an ion starts interacting with a particle. You can spectroscopically investigate these chemical bonds. Molecular details of science that is happening around a particle can be studied. So we do all that. So what's the outcome of all this? I don't want to bore you with a lot of those details as to what we do, but finally what do you get? So what we get are materials with which details are understood. So we studied the process of arsenic removal by materials, and we developed materials of enormous capacity to remove specifically arsenic. So this boy is pumping water in Nadia district in West Bengal. The water is coming from a depth of about 60 to 80 feet. And using this cast iron pump, which is 40 years old, this boy is pumping water. The water that comes out and falls on this cement platform, and you can see at the corner it is red in color. Over a number of years, this red is because of a red stain in water, which is iron oxide. There is nothing so bad about it. We also have iron in our water. But in this region, if there is iron, there is a possibility that there is arsenic in it. The arsenic present is 6 times above the limit. 60 parts per billion arsenic, or 60 micrograms per liter of arsenic is what is present in that water in that region. The limit is 10 parts per billion. So people have been drinking, people have been suffering, and in that region, many different places, you have different varying concentrations of arsenic. It may be 20, 50, 100, 200, even up to 1000. So this is 60. So what do? Well, we can put a solution, and these solutions are known for a long time, but known solutions are not affordable. So as a result, these are not implemented. Now we need to discover new solutions which are affordable. So our thing turned out to be quite affordable, and we supply arsenic free water. And now this is not just arsenic free water. This boy is pumping water, and you can't see it very well. If you focus on that attention, I can't really probably show it here. This water that is falling down is clean water conforming to US EPA standards. Not just arsenic alone, many other things. What's the cost? The cost today is 2.6 paisa per liter. With all costs combined, with capital cost, consumable cost, operator cost, all of these, this is a small unit. It supplies only 1000 liters of water from a bore well with no additional pressure. This boy need not apply a lot of pressure, need not wait for a few seconds to wait that for water to come out. There is no loss of water. All of this is what the technology is about. Materials is one thing, technology is something, field implementation is something, and commercialization is another thing. So you do all that. So finally, this is one such device. You can do this not 1000 liters a day, you can do it 1 million liters a day. You can do 10 million liters a day. So today we supply over 80 million liters of that water every day. Now this is about one technology. Now what's the basis? The basis of all this is from some students. They write some papers and we publish this. So this is in one of our well-known places called Proceedings of the National Academy of Sciences. This boy published this paper along with a few others. It is to say that biopolymer reinforced some composites, which today we call water positive materials. 1 liter of water used for the synthesis of a material, if it produces 1000 liters of clean water in the process of its use in real life, we call it water positive. Why is that? Well, most of these materials, 1 liter of water used for its production, it doesn't produce even 1 liter. The amount of water the material produces is far less than the amount of water it contaminates in the process of production. So they are generally water negative materials. So we introduced a water positive material. The basis of this is biopolymers, over which are fibers like that. As you can see, these are molecular wires over which you create nanostructures. You deposit them, slowly grow them in water, and finally get a water insoluble porous material very similar to the synthesis of, let us say, seashells. Water soluble ingredients, finally water insoluble products, and they stay in the field for extended periods. And this material is like sand, exactly like sand. You put it in water, it doesn't dissolve, although it came from soluble ingredients. And processing is done at room temperature. It is done in water, no organic solvents, no high temperature, and therefore we call it green. And we can ask, what is the water footprint of this product? What is the energy footprint of this product? What is the carbon footprint of this product? All of these questions you can ask, and you say that this material is sustainable. So, okay. So, I have some slide missing. Now, what do we do with this material? This material, you can ask, using this, can you kill bacteria? This picture is to show that it is killing bacteria. Left side is showing live bacteria, right side is showing killing dead bacteria. Now, you also ask, these are nanostructures. You ask the question, do you have, in the process of your cleaning, put nanoparticles into this bacteria? So, you have nanotoxicity. So, for which you evaluate this material. One picture is showing deliberately put bacteria, you are putting bacteria and particles into this bacteria. The bottom is showing bacteria having killed, having lysed, but no particles inside. This is essentially to say that nanoparticles are not there in this process. So, this is one type of material, but that is not the only thing. You have a lot of variety of materials. This is another type of material, and what does it do? Well, some spectroscopy is a particle. On this particle, you can absorb arsenite ions and arsenate ions very well. So, those are tiny dots shown there are ions which are absorbing on the surface. So, what is so great about this? You take a little bit of this material and pass water containing arsenic through that. There is an input arsenic concentration at 200 parts per billion, and what is output? 2 parts per billion. That is what is shown there. How long? With 20 grams of this material, you can run this up to 1,200 liters and arsenic is removed. So, this is to say that in field conditions, in real water, you can create such conditions. So, contaminated water can become clean. So, you can test it in the field. This is a district collector who gave us permission to test it, this particular technology in a ladies' hostel, 250 girls. We did this for about 2 years, and the district collector wanted us to do this in an entire district, that is Murshidabad district in West Bengal, and that is a district map. 100 places in that. By that time, it had become a larger product, and we tested it. So, on the left side that you see, this is several years of struggle and lots of students and lots of money and all that, and all you have to think about all that. So, now on the left side is a traditional treatment plant, 40 cents of land area, supplying about 200,000 liters of water every day. Contaminated water with about some concentration of 200 parts per billion arsenic. Right side, because this technology materials are very much absorbing, you can reduce this 40 cents of land area to 3 cents of land area. Big containers like this on the left side can be reduced to right side 6 inches of containers. So, this is a prototype at that time. Again supplying same quantity of water, about 200,000 liters. Input water concentration of 168 parts per billion, output is 2 parts per billion. Even today it is working. But today it is not working in this form. They are working all over, and they are working like this, and they are working like that. So, there are treatment plants of this kind, and now this is done across the country. What's the cost? 2.1 paisa per liter. Where is it going? It is going to say that you can develop sensors. Each one of these treatment plants, you can put sensors. You can put water quality analyzed, water quantity analyzed. What does that mean? Quality and quantity analyzed on your mobile phone. What does that give you? That gives you analytics, and I will soon come to that. So, today all of this is being done. Now, arsenic is removed. So, arsenic that is removed will be put into a material, right? That material becomes arsenic laden toxic waste. What do you do with that toxic waste? Can you take the toxic waste, come to Chennai? Can you process it? No, we don't want to process it. We want to put this material back into the same soil, because arsenic came from the soil and it has to go back to the same soil. How do we do that? We can do that provided this material doesn't leach arsenic. So we study that leaching and we process that material to be put right in the field itself. So this completes the cycle. So this is an environmentally sustainable solution. So I have a movie here which will not be playing. This is to say that a 2-minute movie to say, hey, how we put this plant, what is it today with all the sensors, and these sensors are displaying water quality online every minute. Data comes to you, water pumps, health is coming to you, electrical power changes, shutdowns, and all this is coming to you, and how much of water is being produced by the station is coming to you, and it is not just coming to you from one plant, it is coming to you from one entire state. And this entire state's water quality is being monitored by a dashboard sitting in Trivandrum or somewhere else at a central location. This is not about Trivandrum, this is about Punjab, and this is about Chandigarh. So you monitor this online. That is an enormous possibility that we have. Let me move further. So this is about situations where water is contaminated, you have to clean it. But if water is not available, what do? You harvest humidity. You know, in air, per person on this planet, we have 1 billion liters of water per person in the air. So we can take a little bit of that. How do you take a little bit of that? So we create a material, and these are nanofibers, metallic nanofibers. They are similar to fibers present on the grass. And in the morning you have seen grass collecting water. Similar thing that we do, that is dew condensation. So we create surfaces such as these on one side, and that is cooled below the dew point. Dew point at this particular temperature and weather conditions is somewhere around 25 degrees. So you cool it to dew point and you collect water, and this is what you see in the morning. This is what you have. And you collect that water, and that's a company called Vayu Gel. And today it produces water 35 liters to 2000 liters per day units. So this is about what's called active water harvesting. You need to put power to collect it. But there are other ways of collecting water. For example, you have a porous material. This at night time, it collects humidity spontaneously. And in the morning, when sun comes up, you warm up this material, and this more material opens up and then releases water. And this is called harvesting. So we have active materials and passive materials. Today this is not a commercial technology, but that is what world has to go to. But there are many other technologies. One other technology is called capacitive deionization. So around the sea, well, we have coastal areas like Kannur, we have seawater intrusion. Water becomes saline. Not in Kannur, but somewhere else. Water becomes saline. Now that water you cannot drink. It is not seawater, but it is brackish water. You need new technologies. One technology is reverse osmosis, but it is not sustainable, as you know. So the best technology in this context is called capacitive deionization, which is electroadsorption. A material which is electrically charged, oppositely charged ions sit on that. So it's negatively charged ions and positively charged ions on another electrode, they both are absorbed and water becomes clean. And the water goes clean, these materials absorb more and more, they get saturated. The potential of these material electrodes is reversed. Then what happens is that the ions absorbed releases, and you collect that ions in water, which becomes reject water. So production rejection cycles you can repeat, and in this process you can produce water. And the whole idea about this is to produce advanced materials which can absorb more. So we have a company to build that. So this can be put in coastal areas where there is a lot of seawater. 70% of Indian population live on the coastal areas. And this can be run on solar because energy requirement is less. And we develop several things, and I don't want to get into the details. So we create materials, we create products, we create companies around this whole theme of advanced materials. I wanted to give you a brief tour of what that is. But that is not the end of it. Look at it in the larger context. You know, world is looking at energy. Energy is coming from petroleum. Petroleum is drying. So what is the next way of energy? Many people think that hydrates is the way. And we have a lecture on hydrates, I heard that in this presentation. These are called burning ice. So these are cages of water in which molecules are contained like methane. And such molecules are produced plenty under the ocean bed. When bacteria decompose, for example, you produce methane. At the ocean bed, there is a lot of pressure and there is a low temperature, and it produces gas hydrates. Gas hydrates are cages of water in which molecules are embedded. You can remove these materials, and when you take these materials out, you can do something called, these materials which are the blue are the materials that gas hydrates. Now, you can break these gas hydrates and get methane and burn it and solve your energy problem. Simultaneously, the broken water molecules give you ice, water, that is clean water. Although it is produced from ocean bed, the hydrate is clean water. So this is called hydrate-based desalination. Some of our friends work in this area. Lots of sensors are important here. So this is an analytical device. Just like your sugar meter, you can measure contaminants in water by a mobile phone. This is not from our work, but with this kind of thing, the entire periodic table has many elements, many of them can be measured. We in our laboratory create sensors too, and these sensors are the ones that are shown there, measuring arsenic quality, very, very low concentrations, measuring that. And these are some details to show that. So where is this going? You are all holding a mobile phone and it has a camera. Can you convert the camera to a spectrometer? And you see that is a spectrometer on the fingertip that is shown there. That's a 4 millimeter thin spectrometer which can measure the optical spectrum in 700 to about 250 nanometers. There are spectrometers of this kind, 4 millimeters. Today, 4 millimeter camera cannot get into this. So people are working on a 2 millimeter camera, spectrometer, can it get into mobile phone? If it gets in, just like what is shown there, I won't be able to show it to you, that water tap, you can shoot a spectrum and collect water quality. And today in our laboratory, we measure spectrum of flowing water. And from that, you create water quality. Imagine where is this going to? Today, you are measuring your water quality before you drink that glass of water. You go home, 100 times you measure that water quality. There are 1 billion people on this planet or this country measuring water quality, and this whole thing is going to become big data. So this is our country, and these are government monitoring stations of water quality. One of those dots, the red dots that you see, the dot, there are 13 villages there, and we monitor water quality in these 13 villages. And one of those villages, water quality is coming on the screen there on the right side. Every minute, water quality is measured. What does this mean? This means that you are getting data of a large kind, and that big data that is coming to you, if it is analyzed well, it is going to tell you whether you will have disease tomorrow. What kind of disease tomorrow? When can you anticipate that? What would be the impact? How can the public system, health system can be prepared for it, how can you have advance warning? This whole system will be called hydroinformatics. And we work on this, developing this hydroinformatics platform for the country. So in order to do all that, when you eat that rice there, you know what that rice contains. Because you know about the water. Because you know about the pesticides. Because you know about the consumables that have been used in producing this product. And you know what would be the impact of this on your people. That way, if you have to prevent it, potential impacts, you have to benefit from those, you have to have a policy. So we influence policy in many ways, and this policy has to be comprehensive. To give you an idea, I don't have that slide. Some years ago, we had, in this country, we had blue cotton, we had red cotton, we had yellow cotton. All these cotton have disappeared. There is no reason to create white cotton, dye it blue, and then contaminate the river and create Professor Pradeep's advanced technology, remove that contaminant. Can you not go back? That means new policy. We have arsenic containing soil. We know that rice accumulates a lot of arsenic. We don't have to have a genetic damage because we eat that rice containing arsenic. And incidentally, genetic damage can happen. Can you have a rice variety which will reject arsenic although it is grown in an arsenic containing soil? We do have that. Nature has given us. Can you work on these? So the policy that I just told you need not necessarily be about technology and technological interventions, but it can also be about our traditional knowledge. And let me come to the end of this talk. Our dreams become reality with materials. This is how I started. What would be the dream of tomorrow be? Can we have a cycle wherein water will drive our society? The same Jules Verne wrote another book in which he asked, one of the characters in this book asked, "Sir, what will you drive tomorrow's vehicles with?" Another character says, "Sir, you will drive it with water." Can you drive tomorrow's world with water? Water producing energy. In the process, of course, it produces water again. It solves both the energy problem and the clean water problem. For this, you need materials. What would that materials be? And these materials have to be affordable, inclusive, sustainable, and contextual, so that excellence can be bred, developed in institutions across. Think about this simple calculation. Hydrogen plus oxygen gives you water. Everybody has studied this. It produces 286,000 joules of energy per mole. This is an exothermic reaction. So what it means is that 1 kg of solar hydrogen can produce a lot of energy. 1 kg of solar hydrogen today is about 750 rupees. But somebody says, our big industrialist says, it can be 150 rupees soon. So I'm taking 150 rupees. It can make 1 kg of solar hydrogen can produce 143 million joules of energy using the same calculation. Desalination needs 2.4 kilowatt hour. That is the kind of energy that is needed for 1 cubic meter of water, which is 8.84 million joules. So that means 1 kg of hydrogen can produce 16.56 cubic meter of water, or 9.06 rupees per cubic meter, or 0.9 paisa per liter. So it is possible, maybe by 2030, when solar hydrogen is affordable, with 0.9 paisa, 1 paisa we can have a liter of water. So, in that process, we will not only produce, well, energy, but also produce water. Well, of course, this is not just thermodynamics alone. You have to have efficiency, other costs of plant and transportation. You can't produce it in Chennai and bring it to Kannur. So, you have to consider all of these aspects. But it is possible that a good possibility is there that water can drive both energy and water for a sustainable planet. And that world would need water literacy. Imagine you are wearing this clothing, there is a water content in it. We are all eating idlis at 5 rupees or something. If you realize very well that 1 kg of rice requires 2000 liters of water, idli will not come with 5 rupees. Well, there is a risk there, but at the same time you will realize that better agricultural practices are required so that rice can be produced not at 2000 liters per kilogram, but with 200 liters a kilogram. That would mean new innovation. This is what I mean by a water literacy. And for that, we have built a center called the International Center for Clean Water, which Sabu and colleagues and your Vice Chancellor visited. This is at the IIT Madras Research Park, and my science is done by several of these people. Manju is also here, I suppose, in this picture. And this is a team which built our Amrit technology. Lots of people, lots of collaborators, lots of partners. And this was all possible because of a great institution. We have built an ecosystem in which innovations become possible. Thank you very much. Questions and all.
Now this session is open for discussion. If you have anything to ask our speaker.
Yeah, go ahead. Shoot. Mike, give the mic to him. Mike.
Maybe my
you are eating, you are drinking water every day.
Yes, sir. Right.
Yeah.
So, I mean, basically, my question is like, because I believe in the principles that matter cannot be created nor be destroyed, right?
Absolutely.
Within that principle, can we create artificial atoms? So that's what my question. So the reason I am asking for this is, for example, you said water is contaminated, right? And maybe it may be with arsenic, iron, and many things. So end of the day, if you look at the primitive levels, that is electrons, protons, and neutrons, right? Can we reassemble those electrons, protons, and these things in maybe of an arsenic component, and can we generate water out of it? So that's what my basic question. And recently, because I read an article in that some scientists have done some research in the graphene or something to create an artificial atoms.
Yeah. Okay. So there are two questions here. So you can create matter. You can create matter from energy. That is what is E equals mc square is. So you can create matter out of energy, but to create matter out of energy, you require a lot of energy. lot of energy, and that lot of energy is not done normally. Therefore, we don't produce matter from energy, we produce energy from matter. This is what we do. So this is one point, and therefore that kind of a technology or methodology will not be effective for something like water, which is needed in large quantities and at very low cost, like no cost at all, right? You essentially want water to be given free to people. The second point is artificial atoms is a kind of thought to understand matter and its properties from principles similar to atoms. For example, some of the nanoparticles, we call them as artificial atoms because they behave like atoms. Certain kinds of nanoparticles have stability similar to argon, neon, krypton, etc. as rare gas atoms. Similar is the case with understanding of artificial atoms. Artificially similar, when you say artificial atoms, you are relating the properties of a larger system to atoms which are simpler. Thank you. Yeah, go ahead. Students, please stand up. Huh? Yeah.
The absorption technique and you talk about capacitive techniques and capture the atmospheric water, etc. We know that the absorptive technique is well known because people are used charcoal for the absorption, charcoal and other things for the absorption. And my question is that so why that absorptive technique that you are projected over here is different from the normal absorptive techniques, because we have high surface area carbon like it is available, which is having more than 1000 meters per gram surface area.
Absolutely, absolutely.
So and it is very cheap also.
Absolutely. So carbon is known for a very, very long time from Mohenjo-daro civilization. Carbon is used for water purification, but the materials, and it's up to 1500 meter square per gram, and all that is there. These carbons remove molecules very well, molecular contaminants. They are essentially good for charge-less species, neutral species. The kind of contaminants that we have, please sit down, arsenic or any such thing, they do get removed by arsenic, by carbon, but to a very, very small extent. The best materials so far people knew were alumina. That is not effective for these kinds of concentrations and at these kinds of contaminant levels. Therefore, traditional materials have not been used for adsorptive removal of contaminants so far. There is also a risk of some of these materials like alumina, because aluminium is toxic as well. So, it comes into water in a very tiny fashion. Even if it is not present in water, it is not effective. So far, although alumina technology has been there for a long time, affordable adsorbents to remove specific things are not there. To give you another example, we are now faced with a big problem of nitrate. Because of a lot of agriculture, nitrate comes in. We don't have any effective adsorbent. There is a lot of technology that's there, but if you are in a position to develop, world is looking for that. Kerala is suffering from another one very major contaminant called perchlorate in certain regions. We don't have materials at all. So, adsorptive technologies, it appears that carbon has been there. All these materials are not like carbon, they're very different in properties. Carbon is not in a position to address many of the challenges.
My second question is the capturing of atmospheric water. Is it economically viable solution?
Yeah, so today it is active methodology. It's a company is there and etc. Many companies exist. Today active methodology is giving you water at 2 rupees a liter. That is the kind of energy cost it is there, even for the best of materials. But tomorrow, I told you which are being tested and all that, these technologies, passive techniques will give you water at something like 10 paisa per liter. And people think that they might even do agriculture with harvested water. That is, a plant will grow with harvested water. So, your technology will be given at the root. It has to simply capture energy, water, and release water at the root. Night time it will harvest, daytime it will release. Okay. Yeah, there is something behind.
Hello. Sir, do you think we can capitalize water-related disasters by some certain methods and to decrease water scarcity levels?
Yeah, calamity is a big opportunity. Capitalize in the sense that, let us say if there is a water-related calamity, flooding, Water has to be, pure water has to be supplied rapidly to affected population, which may be 1 million. There are technologies available. We don't have enough resources to keep all those solutions, 1 million of them, in our storehouse and deploy in every June. There are issues, but you are right that these calamities can be opportunities not only for drinking water but also for storm water. Your every calamity is destroying roads. Can we have advanced materials to protect our roads? Can we develop these technologies from Kerala so that every kilometer that is rain resistant roads, can we get a copyright or a patent or some income from that? So, if you start thinking about water related calamities, it connects you to many things. It floods fields. Can you have submergent resistant rice? There are rice varieties, submergent resistance. Can we improve upon them? We can discuss, okay? Numerous opportunities. പറയൂ. Go ahead, speak.
ഹൈഡ്രോ ഇൻഫോർമാറ്റിക്സിന് കൂടുതൽ പറയാൻ പറ്റുമോ?
വെരി ഗുഡ്. സോ ഹൈഡ്രോ ഇൻഫർമാറ്റിക്സ് എന്ന് പറഞ്ഞാൽ എല്ലാ ഇൻഫർമാറ്റിക്സും പോലെ വെള്ളത്തെക്കുറിച്ചുള്ള ഇൻഫർമാറ്റിക്സ് ആണ്. വെള്ളത്തിൻ്റെ ഹൗ മച്ച് വാട്ടർ വി കൺസ്യൂം, what is the quality of that water we consume, what is the input water from a treatment plant, what is the output water from the treatment plant, what are the diseases prevalent in a population, what diseases are changing in a population. For example, to take this further, it connects to all water related things. Imagine you are living in Chennai and you have wastewater that is there. One person is producing certain liters of wastewater. In a city, a dweller typically uses 130 liters of water per day. And the person is sort of putting out that much of water. If we have a 1 million people, that much of water is coming to the city. This person, 2 people may be COVID affected. Certain other people may be affected by some typhoid or something. The wastewater, which contains water from your toilet, from your bathroom and all that, is containing information about that diseases. It is telling us about how many people are affected in that population. It is telling you how much of these particular antibiotics you have consumed. What new drug that has been developed in America has actually come to India? What would be the kind of economic impact of this drug in the city of Chennai? This whole thing is called wastewater epidemiology. So, water is telling us everything about the economics of a region. Imagine there is Deepavali. On Deepavali day, you have zinc concentration in water going up, aluminium going up. What is the impact of this on people? How many of these have actually come from China versus Shivakashi? All of these is a huge wealth of information. This is what would be called hydroinformatics. So, you just dream. Right? Some of these things that I just told you about, they are all dreams. How do I connect this to the economics of a city? Great opportunity. I have written a paper saying that water will become big data tomorrow. There is one here. പറയൂ, കേൾക്കുന്നുണ്ട്?
My question is, there are so many heavy metals severely polluting our precious water. We are interested in arsenic, even though it is a local issue in West Bengal. And another thing we would like to know, in my place, I belongs to Palakkad, fluorosis, endemic fluorosis is one of the issue there. So is it any economically viable method in terms of defluoridation unit available? Otherwise, is it any nanotechnology helps to prepare such a adsorbent like that? Okay.
Absolutely, good. So I took this example of arsenic to illustrate one story. I work on water in a very big way, so almost every contaminant is being addressed, fluoride is also addressed. Ultimately, people don't want arsenic free water, they want clean water, whether it is arsenic, fluoride, mercury, uranium, whatever, right? So we work on all of these things and provide clean water, so fluoride is available. Now, I worked on this particular issue not because, well, I was not aware of other issues. It is one thing that you got into it, it became larger and larger and larger. And I realized that there is no point in doing some little thing and writing a paper. We have to take it all the way, and therefore it sucks you. You know, ഈ ഒരു ദേവി ഉണ്ടല്ലോ, എന്താണ് സരസ്വതി എന്ന് പറയുന്നത്, suck you. എല്ലാം നിങ്ങളുടെ ഹോമിച്ചാൽ മാത്രമേ എന്തെങ്കിലും കിട്ടുള്ളൂ. അതിനുവേണ്ടി അതുകൊണ്ട് ഈ പറയുന്ന സബ്ജക്റ്റിൽ കുറച്ചുകൂടി ഇൻവോൾവ് ആയി എന്ന് മാത്രം. അതർ തിങ്സ് ആർ ആൾസോ ഗോയിങ് ഓൺ. Economy. Yeah, there. There.
Capacity desalination, such techniques cannot be used for such.
So in the current context, seawater desalination, if that is the objective, at that concentration, capacitive deionization is not economical today. Economical solution as far as that is concerned is reverse osmosis only as of now, but there are other solutions such as thermal desalination. They are also or wind wave energy based, and all of these is going on. We do work on a few of these, for example thermal desalination, but it has not come to a stage wherein you can supply water to the city of Chennai. So there are issues, that is where investment is required. Now, if you were to ask this question as to desalination, what are the options available? Many of these are available, but reverse osmosis has taken up so much because there have been commercial successes and other successes have not been promoted. So if you do that, they will also come up, is what my thought would be. Okay.
Many northern states are adopting your technology and translated.
Yes.
So any implementation in Kerala?
Yeah, Kerala. So right, absolutely, absolutely. So the one of the major Kerala fortunately is blessed with great water, quality water. Our river water can be, we can drink that very well. But Kerala, in several places we have contamination like these iron, huge iron problem in several places, like including Kuttanad, Alappuzha and all. This is where our technologies can be used. So we are discussing with people at that scale.
Sir, the arsenic removal, you are talking about the biocopolymer, right?
Yeah.
So these arsenic will be deposited in that membrane. So how will you removing that one? That arsenic will be deposited again and again.
Yes.
അപ്പോൾ അതിന് റിമൂവൽ പിന്നീട് ബുദ്ധിമുട്ടാവില്ല, എത്രത്തോളം അത് അവിടെ നിലനിൽക്കും?
Yeah, so these materials in general, any adsorbent, our approach is that once it is captured, arsenic being an element, you can't break it. Unlike pesticide or something, we break pesticides. Arsenic cannot be broken. So when it is an element, what you can do is similar to rocks. Arsenic is present in rocks, right? Similar to rocks, you contain them so that arsenic doesn't leach into the environment at larger rates. So because of this particular arsenic containing mineral in the soil, there is an arsenic concentration in water. That is an equilibrium. Your new material should not upset that equilibrium to release more arsenic. This is what we do. So all our materials, even after arsenic uptake, if they go back to soil, they do not release arsenic at an excessively large concentration. Adina nation has put limits. So all our materials work within that limits, not only Indian limits, global limits. ഇതാണ് ഇതിൻ്റെ സൊല്യൂഷൻ. കാരണം ultimately these materials, once they are arsenic uptaken, uranium uptaken, fluoride uptaken, whatever, there is no point in taking that and putting it to your soil or my state or your state, or tomorrow it will be always questioned as to why did I take that particular arsenic from that district and brought it to this district, this village versus that village. This is all happening here now, right? All these questions will come up. Therefore, the right thing is to go back to the same soil but not release. So that's a nation has also adopted that policy. Fortunate to say that. So that's the kind of thought that is there.
Thank you, sir. Second one, atmosphere in the water produce ചെയ്യാന്ന് sir കാണിച്ചുവല്ലോ. ഇത് പിന്നെ പ്രൊഡ്യൂസ് ചെയ്യുമ്പോൾ ഇതിൻ്റെ വാട്ടർ സൈക്കിളിനെ എഫക്റ്റ് ചെയ്യില്ലേ ഇത്?
Very good question. So our number, that's why I gave you this number of 1 billion liters of arsenic is water is present in the air per person. ഒരു ബില്യൺ എന്ന് പറഞ്ഞാൽ മില്യൺ ലിറ്റേഴ്സ് ഉണ്ട്. നമ്മൾ ആകെ എടുക്കുന്നത് 10 ലിറ്ററാണ്. അത് ഇന്ന് എടുത്തു കഴിഞ്ഞാൽ നാളേക്ക് അത് ഉണ്ടാവും അവിടെ. ഇത് വെള്ളം ഉണ്ടാക്കുന്ന പോലെയാണ് അല്ലേ? യു ടേക്ക് ദാറ്റ് വാട്ടർ വിൽ ഇവാപ്പറേറ്റ് ഫ്രം ദ ഓഷൻ. സോ ദിസ് ഈസ് ഓൺലി ടെമ്പററി. കുറച്ച് എടുക്കുന്നു, അപ്പോൾ തന്നെ അത് ഫില്ല് ചെയ്യുന്നു. വളരെ കുറച്ച്. യു കാണ്ട് ഈവൻ മെഷർ ഇറ്റ്. സോ ടൈനി, നത്തിങ്.
വാട്ട് ഈസ് ദ മെറ്റീരിയൽ യു ആർ യൂസിങ് ഫോർ ഇറ്റ്സ്?
ഇതിന് ഇതൊക്കെ കുറേ ഉണ്ടാക്കാവുന്നതാണ്. സോ ദിസ് റിസർച്ച് ഈസ് ഗോയിങ് ഓൺ. സോ വാട്ട് ഈസ് കറൻ്റ്ലി, ടു ഗിവ് യു an idea, what we want is, you want a material which is similar to calcium chloride. Calcium chloride പുറത്ത് വെച്ച് കഴിഞ്ഞാൽ വെള്ളം അബ്സോർബ് ചെയ്യും. അതിനെ ഡെലിക്വസെൻ്റ് മെറ്റീരിയൽസ് എന്ന് പറയും. ഡെസിക്കേറ്റർ. ഇങ്ങനത്തെ ഒരു മെറ്റീരിയൽ വേണം. പക്ഷേ that should work at room temperature. That should work at varying humidities. Humidity at saturation humidity as well as 20% humidity. Diverse range വർക്ക് ചെയ്യണം. ഇവിടെ ഡൽഹിയിലും വർക്ക് ചെയ്യണം, കേരളത്തിലും വർക്ക് ചെയ്യണം. That is one thing. After it is uptaken so much of humidity, when sunlight comes, sunlight will heat this up to about 35-40 degrees. At 40 degrees it should release water. Absorb somewhere around 25-23 degrees, release at 35-40 degrees. അതിന് ഏറ്റവും എഫിഷ്യൻ്റ് ആയിട്ട് റിലീസ് ചെയ്യാൻ പറ്റണം. ദാറ്റ്സ് എ കൈൻഡ് ഓഫ് മെറ്റീരിയൽ ആൻഡ് ടെക്നോളജി ദാറ്റ് വി വാണ്ട്. Our materials that we are working on, we are still working on, you will be commercial only when these materials become really affordable. സ്വർണത്തിൻ്റെ വില കൊടുത്തിട്ട് ആ മെറ്റീരിയൽ നമ്മൾ പെരപ്പുറത്താരും വെക്കാൻ പോകുന്നില്ല. So this should be affordable. അങ്ങനത്തെ affordable, sustainable, recyclable, long lasting, there are all conditions on that, and ultimately this should not impact the environment, right? These polymers tomorrow should not become another problem for us. Okay.
May I ask one more last one? The first slide you showed the water structure with V-shaped.
Yes, yes.
In lower class we studied the hybridization and it is a mathematical concept and it has the hybridization. So is that orbital is really mixing hydrogen and oxygen orbitals are really mixing, and what is the basis of the strongness of that hydrogen bond?
ഇതൊക്കെ ആൾക്കാർ ഇന്ന് people have studied it so well today that you can see a bond. You can see a bond, you can see an overlap, you can see electron distribution. നമ്മൾ പണ്ട് പഠിച്ചിട്ടുള്ള കാര്യങ്ങളൊക്കെയും വളരെ സത്യമായിരുന്നു എന്ന് ഇന്നത്തെ എക്സ്പെരിമെൻറ്റ്സ് പ്രൂവ് ചെയ്തിട്ടുണ്ട്. So you can see a chemical bond. Hydrogen bondന്റെ these are all concepts, right? ഈ concepts ഒക്കെയും ഇന്ന് they are proven with experimental observations. So p orbital today, you say p orbital, can you see it? Yes, people have seen it. Orbitals can be seen today. അപ്പോൾ ആ കാണിച്ച പിക്ചർ വളരെ സത്യമായ പിക്ചറാണ് എന്നാണ് എനിക്ക് പറയാനുള്ളത്. ഇത്രയേ ഉള്ളൂ. They are mixing. But mixing is our understanding, right? Mixing is our understanding. It's a composite orbital.